When dealing with transformer overcurrent protection, it is important to understand the relevant sections of the National Electrical Code, specifically 250.66 and 250.122. The scenario involves a 150 kVA transformer fed from a 200 amp, 3-phase, 480 volt breaker on the primary side, supplying a 208/120 volt 3-phase feed to a 400 amp panel board. The core of the matter revolves around sizing the overcurrent protection on the secondary side of the transformer, particularly when the exact breaker size immediately after the transformer is unknown. This situation brings into play the application of NEC section 250.66 versus sizing based on 250.122, using the 400 amp breaker size as a reference. Let's delve into the arguments and considerations surrounding this topic. Firstly, if there is no breaker immediately after the transformer on the secondary side and the actual breaker size is unknown, one approach involves adhering to the maximum load current permitted by the 250.66 rule. This rule often dictates sizing the overcurrent protection device at 125% of the transformer's rated current. In this particular case, the transformer is rated at 150 kVA. To calculate the maximum load current, you would multiply 150 kVA by 1.25, resulting in 187.5 amps. Using a 400 amp breaker in this scenario would exceed the maximum load current determined by the 125% rule. Consequently, a 400 amp breaker might not be considered a suitable overcurrent protection device based on a strict interpretation of this approach. Secondly, there is an alternative perspective. The 250.122 rule, which allows for 100% of the transformer's rating, can still be applied even if the exact breaker size is not known. This is contingent upon ensuring that the branch circuit conductors are appropriately sized to handle the maximum load current dictated by the 250.66 rule, which, as previously calculated, is 187.5 amps. In other words, the conductors feeding the 400 amp panel board need to be capable of safely carrying at least 187.5 amps. Given that the panel board is rated for 400 amps, it inherently possesses the capacity to handle the maximum load current allowed by the 250.66 rule. Therefore, proponents of this viewpoint argue that a 400 amp breaker could indeed serve as suitable overcurrent protection. Now let's reconcile these seemingly conflicting perspectives. The crux of the issue lies in the interplay between conductor sizing and overcurrent protection. Both the 250.66 rule and the 250.122 rule can be legitimately employed to determine the appropriate size of the overcurrent protection device. However, the deciding factor is whether the branch circuit conductors are sized adequately to accommodate the potential load. In this specific instance, both a 250 amp breaker and a 400 amp breaker could be deemed acceptable, contingent upon the proper sizing of the branch circuit conductors. It's crucial to understand the calculations behind these decisions. The transformer's secondary current can be calculated using the formula E equals S divided by V times the square root of 3, where I represents the current in amps, S represents the apparent power in volt amps, and V represents the voltage in volts. For a 150 kVA transformer with a 208 volt secondary voltage, the calculation would be I equals 150,000 volt amps divided by 208 volts times the square root of 3, which equals approximately 416.5 amps. The 125% factor from NEC 250.66 would then be applied to this value, resulting in 520.625 amps. However, this calculation is used for grounding electrode conductor sizing, not necessarily for overcurrent protection directly on the secondary side. NEC 450.3 provides guidance on transformer overcurrent protection. For transformers with overcurrent protection on the primary side only, the secondary overcurrent protection is typically not required if certain conditions are met. If secondary protection is desired or required, 450.3b outlines the requirement. Generally, the secondary overcurrent protection should be set at no more than 125% of the transformer's rated secondary current if the primary overcurrent protection is sized according to the code. For the primary protection, if the transformer has a primary current less than 9 amps, the overcurrent protection device can be set at no more than 167% of the primary current. If the primary current is 9 amps or more, the overcurrent protection device can be set at no more than 125% of the primary current. In our scenario, the transformer is fed from a 200 amp breaker, which is well within the allowable limits for primary protection. Now, focusing on the conductor sizing, NEC 310.16 and associated tables are essential for determining the appropriate conductor size based on the ampacity requirements. The conductors must be sized to carry the calculated load current, considering directing factors for ambient temperature, number of conductors in a raceway, and other relevant conditions. To elaborate, let's consider the steps involved in determining the appropriate overcurrent protection and conductor sizing for the transformer secondary. Firstly, calculate the transformer's rated secondary current. As we determined earlier, this is approximately 416.5 amps for a 150 kVA transformer with a 208 volt secondary. Secondly, determine if secondary overcurrent protection is required or desired based on NEC 450.3. If the primary is protected and meets the code requirements, secondary protection might not be mandatory, but it is often recommended for enhanced safety and protection of the downstream equipment. Thirdly, if secondary overcurrent protection is selected, size it according to 450.3b. Typically, this involves selecting an overcurrent device rated at no more than 125% of the transformer's rated secondary current. In this case, 125% of 416.5 amps is approximately 520.625 amps. Therefore, the next standard size breaker below this value would be selected. However, the available tap rules and specific installation requirements can influence the final selection. Fourthly, size the conductors according to NEC 310.16, ensuring they have an ampacity equal to or greater than the calculated load current, which is based on the transformer's secondary current and any applicable demand factors. The conductors must be protected by the overcurrent protection device, and the overcurrent protection device must be sized to protect the conductors. This often involves considering the standard ampacity ratings of conductors and selecting the appropriate size that meets or exceeds the required ampacity. Now, let's address the specific arguments presented in the scenario. Firstly, the argument that a 400 amp breaker would exceed the maximum load current allowed by the 250.66 rule is based on the assumption that the 250.66 rule dictates the overcurrent protection size. However, 250.66 is primarily related to grounding electrode conductor sizing and not directly to overcurrent protection. The overcurrent protection is governed by NEC 450.3 and 240.4. Secondly, the counter-argument that the 250.122 rule can be used if the branch circuit conductors are sized for the maximum load current allowed by the 250.66 rule is partially correct. The 250.122 rule pertains to equipment grounding conductor sizing, which should be sized based on the rating of the overcurrent device protecting the circuit. The key is that the conductors must be sized appropriately for the load, and the overcurrent protection must protect those conductors as per NEC 240.4. In conclusion, the selection of the appropriate overcurrent protection device for the transformer secondary involves a comprehensive understanding of NEC 450.3, 240.4, and 310.16. While a 400 amp breaker could potentially be used if the conductors are adequately sized and the primary protection is in accordance with the code, it's crucial to verify all requirements and calculations to ensure compliance and safety. The best practice is to follow the specific guidelines in NEC 450.3 and select an overcurrent protection device that is appropriate for the transformer's secondary current and the conductor ampacity. Always consult with a qualified electrical engineer or inspector to ensure compliance with local codes and regulations. The following points summarize the key considerations. 1. Calculate the transformer secondary current. 2. Determine if secondary overcurrent protection is required based on NEC 450.3. 3. Size the overcurrent protection device according to NEC 450.3b. 4. Size the conductors according to NEC 310.16, ensuring they are protected by the overcurrent protection device. 5. Verify all calculations and requirements with a qualified professional. In addition to the NEC requirements, it's important to consider industry best practices and safety standards. Overcurrent protection is designed to protect equipment and personnel from the hazards of overloads and short circuits. Proper selection and installation of overcurrent devices are critical to ensuring the safe and reliable operation of electrical systems. The use of appropriately sized overcurrent protection devices helps to prevent damage to transformers, conductors, and other electrical equipment. It also helps to reduce the risk of electrical fires and other hazards. When selecting overcurrent protection devices, it is important to consider the specific characteristics of the transformer and the load it serves. Factors such as the transformer's kVA rating, voltage, and impedance should be taken into account. The load characteristics, such as the type of equipment being powered and the potential for overloads, should also be considered. It is also important to ensure that the overcurrent protection devices are properly coordinated with other protective devices in the electrical system. Coordination helps to ensure that the correct overcurrent device will trip in the event of a fault, minimizing the impact on the rest of the system. Proper coordination can also help to prevent nuisance tripping of overcurrent devices. Regular maintenance and testing of overcurrent protection devices are also essential to ensure their proper operation. Overcurrent devices should be inspected periodically for signs of damage or wear. They should also be tested to verify that they are tripping at the correct current levels. Any damaged or malfunctioning overcurrent devices should be replaced immediately. Finally, it is important to follow all applicable electrical codes and regulations when selecting, installing, and maintaining overcurrent protection devices. The NEC provides detailed requirements for overcurrent protection in transformers and other electrical equipment. Local codes and regulations may also impose additional requirements. Compliance with these codes and regulations is essential to ensuring the safety and reliability of electrical systems. In the context of the scenario, a detailed review of the specific installation conditions, including the transformer's nameplate data, conductor types and sizes, and local codes, is necessary to make a final determination on the appropriate overcurrent protection. It is also important to consider the potential for future load growth and to select overcurrent protection devices that can accommodate these future needs. In addition to the technical aspects of overcurrent protection, it is also important to consider the human factors involved. Electrical workers should be properly trained on the safe selection, installation, and maintenance of overcurrent protection devices. They should also be aware of the potential hazards associated with working on electrical systems and should follow all safety procedures. A thorough understanding of overcurrent protection principles combined with proper training and adherence to safety procedures is essential to ensuring the safe and reliable operation of electrical systems. In summary, the seemingly simple question of overcurrent protection for a transformer involves a multifaceted analysis of electrical codes, equipment characteristics, and safety considerations. A proper understanding of these factors is critical to ensuring the safe and reliable operation of electrical systems. The selection of the appropriate overcurrent protection device should be based on a comprehensive assessment of the specific installation conditions and a thorough understanding of the relevant electrical codes and regulations. Consultation with a qualified electrical engineer or inspector is always recommended to ensure compliance and safety.